Tesla's 2026 Model 2 is shaping up to be the biggest EV breakthrough yet. A $17,000 car capable of reaching 620 miles on a single charge. The secret lies in Tesla's bold battery strategy. Two cutting-edge chemistries: aluminum-ion for ultra-fast charging and solid-state for record range and safety. Backed by new data from Tesla's Nevada labs, this move could reset global EV standards. Let's dive right in. For the first time, Tesla isn't betting on one technology. It's developing two entirely new chemistries in parallel: aluminum-ion and solid-state. One is almost ready for mass production. The other could redefine the industry for decades to come. While the industry still wrestles with the high cost and geopolitical risk of lithium and cobalt, Tesla quietly turned to something far more abundant: aluminum. Cheap, lightweight, and widely available in North America, aluminum gives Tesla one thing lithium never could: independence. According to recent reports and patent filings, Tesla's new aluminum-ion cells use a multi-layer stacking technique with ultra-thin 0.5mm foils. By increasing the number of energy layers without adding mass, Tesla achieves an 80 kilowatt-hour battery pack capable of around 380 miles of range. Remarkable for a low-cost EV. But range isn't the only surprise. These cells can charge up to 15 times faster than today's lithium-ion packs, reaching 80% in 3 minutes and a full charge in just 5. That's faster than refueling a gas tank. And it's backed by lab test data from Tesla's own R&D division. Because aluminum is 30% lighter than lithium, this denser design doesn't add bulk. It actually makes the car lighter and more efficient. The result? Better handling, lower tire wear, less cooling demand, all translating into reduced lifetime costs for owners. And the strategy behind it is brilliant. By sourcing aluminum directly from Nevada and Utah, Tesla eliminates foreign dependency. With 7 million tons of local reserves, the company can power over 3 million Model 2s without importing a single gram of lithium or cobalt. Tesla's partnership with Graphene Manufacturing Group takes it even further. They're building graphene-enhanced aluminum anodes with a nano-honeycomb structure, boosting conductivity and narrowing the energy density gap with lithium-ion. If successful, this innovation could bring pack costs down to just $3,000 compared to today's $7,500 lithium battery. That's the foundation of the $17,000 Model 2. Not marketing hype, but genuine engineering economics. But Tesla isn't stopping there. While aluminum-ion is the near-term disruptor, solid-state represents the long-term crown jewel, a cleaner, safer, higher-capacity solution that could eventually dominate the EV landscape. Inside sources say Tesla's prototype solid-state cells are achieving energy densities around 500 watt-hours per kilogram, nearly twice that of lithium-ion. Without any liquid electrolyte, they're immune to overheating and fire, with thermal tolerance up to 752 degrees Fahrenheit, 400 degrees Celsius. That's a full 250 degrees Celsius higher than conventional lithium batteries. Durability is where solid-state truly shines. These packs are designed to last over 10,000 charge cycles, potentially outliving the car itself. No swelling, no leaks, no degradation panic. After 10 years, drivers could still retain 90 to 95% capacity, making battery replacements nearly obsolete. Tesla plans to build these using its existing dry electrode 4680 production lines, a major cost advantage over rivals like Toyota or QuantumScape. By adapting current manufacturing to handle sulfide-based solid electrolytes, Tesla avoids massive retooling costs while gaining a 2 to 3 times improvement in energy efficiency. A 60 kilowatt-hour solid-state pack could push the Model 2's range beyond 620 miles per charge, while making it 40% lighter. That reduction lowers the car's floor height, increases interior volume, and enhances responsiveness, enabling 0 to 60 miles per hour under 4 seconds in the performance variant. So, Tesla's strategy becomes crystal clear. Aluminum-ion powers the standard Model 2. Affordable, fast-charging, mass market. Solid-state powers the Model 2 performance, premium range, ultra-safety, and elite efficiency. 2 technologies, 2 market segments, 1 mission, total EV dominance. Specs on paper are one thing, but Tesla's true challenge is real-world performance. Extreme heat, deep cold, constant charging, daily wear. Here's where the new chemistries stand apart. Traditional lithium batteries start breaking down around 250 degrees Fahrenheit, leading to gas expansion and fire risk. Aluminum-ion's gel polymer electrolyte, by contrast, remains stable until 572 degrees Fahrenheit, nearly twice as high. That makes it 99% less likely to catch fire, even under abuse or collisions. Solid state takes that safety further. With a ceramic sulfide electrolyte, it can handle 752 degrees Fahrenheit without chemical decomposition. No flammable liquids, no explosion risk, no need for bulky cooling systems. Longevity follows the same pattern. Lithium batteries typically last 1,500 to 1,800 charge cycles, about 6 years of daily use. Aluminum-ion stretches that to 5,000 cycles, roughly 15 years. Solid-state doubles it again to 10,000 cycles, effectively making EV battery degradation a thing of the past. This durability has ripple effects everywhere. Insurance premiums drop because the risk of thermal incidents or total losses plummets. Maintenance costs fall thanks to fewer moving parts, pumps, and coolant systems. Even resale value improves because buyers no longer fear buying a used EV lottery ticket. And when these packs do retire, Tesla already has a plan. Aluminum-ion cells can be recycled easily and reused for home energy storage, turning old car batteries into backup power for homes. Solid-state packs, with their ultra-pure cathode materials, are perfect for commercial microgrids or vehicle-to-grid V2G systems. In short, every Model 2 battery lives twice, once on the road, once as energy infrastructure. Innovation only matters if it scales. That's why Tesla's battery roadmap is not just about technology. It's about production flow, cost curves, and supply logistics. Aluminum-ion manufacturing is inherently simpler. Its stacked foil architecture requires fewer cooling channels and no liquid containment. That allows robotic assembly lines to run faster and cheaper, reducing capital cost per gigawatt hour. Each new gigafactory can replicate this model rapidly. And since aluminum refining and recycling are already widespread in the US, Tesla's domestic supply chain becomes nearly self-sufficient. This efficiency translates directly into a lower sticker price, and more importantly, a price that stays low as production scales. Solid state, however, is the marathon runner. Its early stages require strict environmental control, dry rooms, ceramic handling, and high-yield precision. But once production stabilizes, the benefits compound. Smaller packs, lighter platforms, and reduced shipping costs per mile of range. By 2027 to 2028, Tesla expects solid-state production costs to drop below $90 per kilowatt-hour, down from $130 today. At that level, Even premium EVs become profitable at mass scale. That's the heart of Tesla's dual-phase strategy. Use aluminum-ion to dominate the market fast. Affordable, scalable, and ready by 2026. Transition to solid-state once yields and costs align, enabling higher margins and longer product cycles. It's not one versus the other. It's evolution in motion. Zoom out, and you'll see Tesla's real move isn't just about batteries, it's about control. Control over materials, control over costs, control over the future of energy itself. By building both battery chemistries domestically, Tesla cuts the final dependency thread from Asia's lithium networks. It also creates a closed-loop system, where aluminum scraps from vehicle production feed directly back into new anodes. Each Model 2 built strengthens the next. A self-reinforcing manufacturing ecosystem. If successful, the Model 2 won't just be a cheaper Tesla. It'll mark the moment when EVs become mainstream economics, not luxury exceptions. A car that costs less than $20,000, charges in minutes, lasts decades, and drives over 600 miles. That's not just a milestone for Tesla. That's the beginning of a new energy order. And that's why every automaker, from BYD to Toyota to Volkswagen, is watching nervously. Because once Tesla flips this switch, the price floor of the EV industry changes forever. So, what do you think? Will aluminum-ion take the crown with its speed and affordability? Or will solid-state eventually rise as the ultimate battery revolution? Share your thoughts below. Which future would you choose to drive? And this, right here, is exactly why the Model 2 could mark the single biggest turning point in Tesla's history. What we're witnessing isn't just the birth of a new EV, it's the moment where battery innovation, affordability, and energy independence finally intersect. Because if Tesla can deliver a $17,000 car with a 620-mile range, it means something much bigger. Clean energy is no longer a luxury. It's the new standard. And this breakthrough doesn't stop at the road. The same chemistry that powers the Model 2 could one day power lunar habitats, Mars rovers, or the next generation of spacecraft, proving that innovation on Earth fuels exploration beyond it. But this is only the beginning. The next 24 months will decide which battery, aluminum-ion or solid-state, shapes the future of mobility. Will we choose speed and scale, or endurance and perfection? What do you think this shift means for the entire EV industry and for humanity's push toward a sustainable interplanetary future? Share your thoughts below. This is Tech Revolution, where we decode the breakthroughs shaping tomorrow. If you want to stay ahead of what's coming next, you know where to find us. Because the future isn't waiting, and neither should we.